All right, so we have a function y equals x to the power of x here, and this is the pattern that we see. So as x goes down from 1 to very, very close to 0, and takes this sort of form like 0 to the power of 0, instead of becoming 0, it actually approaches 1. So for this bit over here, we see that 0.00001 to the power of 0.00001 is this value right here. So why does it, so we're starting from here, this is 1 to the power of 1 to the power of 1 is 1. So starting from there, it seems to decrease, and then there is a turning point there, and turns around, and then goes to approach 1. So I'm going to provide one reason from point of a differential calculus why there is such turning point there. So from basic calculus, we know such thing called a stationary point. So to find stationary point, what we need to do is take derivative, and then we let it equal 0, and then we solve for that. For example, if you have y equals to x squared, to find the stationary point, then we take the derivative, which is the f dash of x, that's 2x, and you let that equal 0, and then you solve for x, and x must be equal to 0. So that's the reason why this x squared, y equals x squared function has stationary point right there. So how do we differentiate? So if the original function is x to the power of x, how do we take differentiation of that? The answer is not. So the answer is not. So a lot of people assume that it's going to be x coming out to the front and x to the power of x minus 1, but that's not the rule that's applicable to this situation, because that rule, like lowering the power and then taking minus 1 from subtracting 1 from the power, that's only applicable when the exponent is a constant, right? So we cannot do that. Rather, what we need to do is what's called an implicit differentiation. Implicit differentiation. First, we need to write, you have y equals to x to the power of x, and then you have to take log on both sides. So taking log both sides is not part of implicit differentiation. You just do that. You just change the equation into ln x to the power of x. So natural log y, natural log x to the power of x. And naturally this x comes out to the front. So this is one of the log rules. This is not the differentiation rule at all. So this x comes out to the front completely. So there's no more exponent there. And now you do what's known as implicit differentiation. So I'll show you what implicit differentiation is. So when you have like a circle equation, y squared x squared equals to, let's say, 9. So that's equation of a circle with a radius of 3, right? And if you want to take differentiation of this and then find the gradient at any point, then what you need to do is what you would normally do if you do explicit differentiation, then you have to rearrange that equation. So y squared equals to 9 minus x squared, and then take plus and minus square root 9 minus x squared, and then if you differentiate that, let me just take positive value. So positive root is just the upper function over here. The negative is the lower function. So that's negative and positive. I'm just going to differentiate just the positive function, okay? The upper function. So that's positive, and then I'm going to write this as 9 minus x squared to the power of half. Now what you need to do, in this case, of course, this is now explicit expression. Y is on one side, everything else is on the other side. So you have dy dx, the derivative, half comes out to the front, 9 minus x squared, and then you take minus 1 there, so you get negative half minus 1 is a negative half, and then you have to times it by the differentiation of the bracket by the chain rule, so it's a negative 2x, right? And then this simplifies down to, so 2 and 2 cancels out, negative sign survives. This one here, negative sign, you have 2, sorry, 2's are gone, and you have x over here. And this one becomes positive exponent by going to the bottom, so this will be 9 minus x squared to the power of positive half, but then that can be changed to square root, right? So that's square root of 9 minus x squared. So this is how you do explicit differentiation. Now the implicit differentiation of implicit differentiation is you can just differentiate straight off from this one here. So what you need to do is, if you want to differentiate y squared, just treat y as if it's just x. So if it's x squared, then it becomes 2x, right? So it becomes 2y. And whenever you differentiate y, just have to put dy dx next to it. Okay, so that's the rule. And then you have 2x there, so differentiate that. And differentiation of 9 is 0. And then you rearrange that, you can find dy dx. That's 2x over 2y. So this cancels out, you get negative x over y. Well, let's compare this one with this one. Are they identical? This one says dy dx is this one here. It's in terms of x only. Here, it only took 2 lines to do it. But is this really correct? Let's double check. So if we plug back the y value, y is given by this one, isn't it? So substitute that over here into over here. Then you get square root of 9 minus x squared, which is exactly the same thing as this expression over here, right? So this is how easy implicit differentiation is, okay? Now, if you differentiate log of y, so differentiation of log of x is, ln of x is 1 over x. So this turns into 1 over y. And then you have dy dx. So that's the rule. So for implicit differentiation, you just differentiate as if y is just x. And then you just have to put dy dx next to it whenever you're differentiating in terms of y. And then this one here, you got to use a little bit of product rule. So differentiation of that is 1 times by ln x. Differentiation of this one is 1 over x, so this is x times by 1 over x. So that cancels out, become 1. So that's equal to ln x plus 1 dy dx. And you have dy dx equals to y ln x plus 1. And of course you can write y in terms of x. We know that y is x to the power of x, so that turns into x to the power of x, and then x ln x plus 1. Now, to find a stationary point, you have to let that equal 0, right? And if this expression is 0, neither that must be 0, and that must be 0. So, well, for this one, I don't know how to make that 0. But I know how to make this part 0. So just let ln x plus 1 equals 0. Then you get ln x equals minus 1. This is base e here. So e to the power of negative 1 is x, which is also the same as 1 over e. E to the power of negative 1. That just turns into this one. And turns out this value is, let me just bring the calculator here, 1 over, that's 0.36788. Okay, so it turns out this value is the stationary point that gives you the minimum. So there must be a turning point. So this value over here is this value right here. Okay. And of course, there are many other aspects you can learn from this function, but I just wanted to mainly focus on the stationary point right there. Okay, and of course, you can check whether that's a minimum point or maximum point by doing double derivative or using sine table, whatever. Okay, so anyway, that provides a turning point, and the turning point is 0.36788.